are bigger than the finishing time of this professor. Now the finishing time is 6, so we have to look at all the jobs whose starting time is bigger than 6, and there's only one. That's Professor 8. So this is what we get. This is how we schedule these guys. Now, this is a greedy algorithm, because what you're doing in this algorithm is you're maximizing a local function. The local function is I'm trying to take the next professor. So once I have sorted the finishing times, every time I want to schedule a professor, I take the next one possible. That's the algorithm. Take always the next one possible, because the next one possible is exactly the professor whose starting time is bigger than or equal to the finishing time of the previous professor. Yes?
In which sense is this function local?
Because you don't look at all the professors. You don't look at the things that will be coming your way, way in the past, way in the future. You just look at your finishing time and take immediately the next one whose starting time is. It could be, the theorem says that this is not possible, but it could be that if you took maybe something much bigger, that at the end you would have a better utility function. But the theorem says no. The theorem says this is the best you can do. Or not the best, but the solution you get is a largest subset. The solution is not necessarily unique, but you cannot get a solution where you can schedule more than, a subset with more professors than this. Yes, please.
What if you take the starting time in consideration?
I'm sorry?
What if you take the starting time in consideration of the professors?
If you take the starting time in, okay.
For instance, after the professor one finishes, you can start the professor.
Okay. So that doesn't always work. And maybe that doesn't always work. Maybe in this example it does, but in general it doesn't work. In general, I don't think you can get the best subset this way. But for that, we need to actually, the proof tells you a bit more about this. So the question is this algorithm optimal? You remember, by the way, this optimal coin algorithm. You remember that in one of our earliest classes? So there, you have coins of certain values, and you have a you want to create, you want to give to someone some amount of money, and then you want to take the smallest number of coins whose sum is equal to that amount. You remember that algorithm? That is a greedy algorithm, because there we said, well, we take the largest coin, as many times as we can until we can't take some coin of that value. Then we take the next largest and the next largest and the next largest. This is a typical greedy algorithm. And this algorithm is not always optimal. There are cases where you can show that the algorithm is not optimal. Does that answer in which case this is greedy? Do you get a sense of what a greedy algorithm is? You really locally try to optimize your utility function. There is a great thing about greedy algorithms. Because you don't look at the entire data, but maybe just the next one that comes your way. If the data that you're getting is not even present at the time you start your algorithm, you could use that, because you just deal with your data the minute it actually arrives. You don't have to do some big here you do some pre-processing on the data because you have to sort the finishing times. But with the optimal coin problem, you don't have to do even a pre-processing. Right? So if somebody maybe in the process of trying to give the next value, you get a different coin with a completely different value, you can just immediately integrate it into your algorithm and off you go. That's very good. And these kind of algorithms where you deal with the data as it is coming in are called online algorithms. And these are very important algorithms in data streaming and a lot of things that are happening on the internet, for example. But anyway, that's not the topic here. The topic is to show that this is an optimal algorithm. Okay. So in other words, the subset that you get is the biggest subset that you can possibly get. Okay. So the very first thing to show is, our algorithm. What does our algorithm do? At the very least, the first job, the first professor, the professor with the smallest finishing time, will always get scheduled in this algorithm. So maybe, a good thing to show is that whenever you have an optimal solution, you can always massage this optimal solution in a way such that the first professor is scheduled, is part of this subset. So in other words, so the theorem says that the greedy algorithm is optimal for the scheduling problem. Okay? And the proof is as follows. So we show that in a first step is, what we show in a first step is that there is an optimal solution, an optimal subset of 1 through n, which contains the element 1. It doesn't say that any optimal solution contains the element 1, but it says there is one that contains the element 1. Why? So there is a proof of this. And the proof is given over there. So we take an optimal solution, okay? And we take k to be the minimum of the finishing times when I is in this set. So we take the optimal solution, we take the smallest finishing time in this optimal solution, and we call it k. Now obviously if k is 1, then we are done. I'm sorry. It's not k, I'm sorry. Actually, do you know this argmin? Do you know what argmin means? No? Okay, so now I need to define that. Argmin is not the minimum, but is the index of the minimum fi. So let me just write it again for you. So k is the index of the smallest fi where I is in A. That's the index of that smallest fi, not the fi itself. It's index. Okay? So if you have already ordered your fi, this would correspond to the smallest element of A. That's the same thing. Now if k is 1, then of course 1 would be an element of A and we would be done. So that's it. So we can assume that k is not 1. If k is not 1, well, it has to be larger than 1. Then we construct another subset. The subset is called A prime, and this A prime you obtain by removing k from A and replacing it with element 1. So replace k by 1 in A. That's what A prime is. Well, certainly we know that F1 is less than or equal to Fk because we have ordered the F's. Because F1 is the minimum of all Fi, I from 1 through n. Agreed? So what does it mean? Does it mean, so first of all, A prime is a valid solution. A prime is a valid solution. That means there is no conflict of scheduling if you take elements in A prime. Why? The only possibility for a conflict of scheduling is when there is a starting time in A prime that is smaller, how can I put it? So there is a starting time in A prime that's smaller than this F1. No? That's the only possibility. But this is not the case because, you see, for all L in A, we know that the starting time, and L in A and L, not K, we know that the starting time, SL, is bigger than the finishing time, Fk, because A is a valid solution. You cannot have a starting time before. So therefore, A prime doesn't have conflict. So therefore, A prime is a valid solution, and A prime is an optimal solution because it has the same size as an optimal solution. It's an optimal solution containing 1. So this proves this one. This proves that there is an optimal subset which contains 1. That's A prime. Okay, the next thing we are going to do is we are going to reduce the problem to one which has n minus 1 professors rather than n. We got rid of one of the professors because it's scheduled and so on, so we're going to reduce the problem to a case when this one professor has disappeared. So we are going to use a new subproblem. Namely, we are going to set a new set S prime, which is the set of all instances for which the finishing time is greater than or equal to the starting time is greater than or equal to the finishing time of the first professor. So once we have scheduled the first professor, now we are going to look at all the other professors that don't have a conflict with this first professor. And their indices are in this set S prime. So if we take this A prime solution or A solution, so A is optimal solution of original problem with 1 A contained 1 is in A, then we know that if we take A and take 1 out, this becomes an optimal solution of S prime. That is the key to the proof that this thing is optimal. Why? You see, we have now gotten rid of the first professor. And we are going to look at the situation where, we are looking at the other professors that are in this optimal solution. This one, if this was not an optimal solution for S prime, there would be a solution in S prime with even bigger number of professors. Right? Otherwise, there exists a solution B to S prime with the size of B strictly bigger than the size of A plus 1, minus 1, which is the size of this set. But then, if we add element 1 to B, we get a solution of the original problem. And its size would be the size of B plus 1, which is strictly bigger than the size of A. But A was an optimal solution. You cannot find another solution whose size is bigger than the size of the original solution. So this is a contradiction. So the key to this greedy algorithm is, or to the analysis of the greedy algorithm, is to say that once, you see, what the greedy algorithm here is doing is the following. It schedules the first professor, and that's it. It never ever looks at this first professor again. That's it. That's, this guy is scheduled, and no matter what data comes later, this one professor will stay where this professor is. And then the next time a professor is scheduled, we are never ever looking at that again. That's it. So this means that once we have scheduled a professor, we have taken that professor out, and together with everyone whose starting time is smaller than the finishing time of this professor. And then we have a new instance of the problem. That's how this greedy algorithm works. And what this is showing is that if we do that, if we take this professor out and look at the new solution and find the optimal solution there, then if we add this first professor back in, we get the optimal solution of the original problem. And that is why the algorithm works. That's why the solution to this algorithm is optimal. Is it sort of clear? Okay. So, important, there is never a general recipe for creating a greedy algorithm. That does not exist. You have to really, from case to case, you have to look at what you're doing. And there are two elements to this greedy algorithm. There is the greedy strategy, which is really based on the following: that the global optimum can be obtained by doing very local decisions. And then, if you want to prove that this is correct, you have to show that certain substructures of this algorithm, if you do this, are optimally solved with the greedy algorithm. So in this case, the substructure was one in which we took out all the professors with starting time smaller than the finishing time of the first professor. And this new subinstance, we showed that this, that's an optimal solution of this can be extended to an optimal solution of the original problem, and that way we could solve the the optimality issue. But there is no general recipe for that. What we are going to do is, I'm going to show you 3 examples in this chapter. I've already shown you one. I'm going to show you a second one that is not that difficult still. And then I'm going to show you a third one that's called Huffman coding. That's something that you should really know how to do, what a Huffman code is and how it works. Okay? But the Huffman coding we will do on Monday, not today. All right, next problem. Next problem is really the dynamic programming. This dynamic programming problem we had for the knapsack. So in the knapsack problem, you remember the knapsack problem? So we had n items. Each item had a value and a weight. And we wanted to find, and then we, on top of it, we had a weight budget. We wanted to find the biggest subset of these items, or actually a subset of these items, not necessarily the biggest, a subset of these items, such that the total weight of these items in the subset does not surpass the weight budget, and the total value is maximized. That was the knapsack problem. It's also sometimes called the 0-1 or combinatorial knapsack problem, in the sense that we could not take half objects. We had to take one full object every time. Okay? Now in this version over here, we are allowed to take half objects or quarter objects or fractions of an object. So you can imagine, if I go back to the analogy of going on a hike and you want to take water, well, maybe you don't want to buy bottled water, but maybe you have a bottle yourself and you want to fill it with half of it full, not completely full, or just a quarter of it full, not completely full. So with water we can do this. With bread we can do that too. You take just a fraction of the bread, and so on. But with books it becomes a bit more difficult and these objects. But anyway, so in this new version of the problem, we do the following thing. So this is the rational or continuous or so we have n objects. We have values of the objects are v1 through vn, and we have weights w1 through wn, and we have a weight budget so maybe all these are just numbers. So in the original knapsack we wanted to find a subset of the budget of the items that would maximize the value. Here we want to find a rational combination of the objects. So find zero x1 up to xn between 0 and 1 such that x1 times v1 plus xn times vn is maximized subject to x1 times w1 plus xn times wn is less than or equal to w. So here, you see when the xi's are only allowed to be 0 or 1, we get back the original knapsack problem. Here, we are allowed to take fractions of items. And the x's tell us which fraction. If x is, for example, a half, it means we take half an object. If it is a tenth, it means we take 1/10 of an object. Now, can you imagine that this is easier than the original knapsack problem? You can? Why? Why do you think it's easier? Yeah?
Because you just have to take the objects which have the more values for...
Yeah, this is the algorithm, yes. This is the algorithm that we need to prove, yes. Yes, so is there an intuition why this could be easier? Yes?
You can always obtain the maximum weight because you can take fractions of objects.
To get the maximum weight, yes. You could always get, yes. That is somewhat an intuition. What did you want to say?
Take very small xi's, for example. Take just a little bit of everything. Very small. For all x is small.
Yes.
And we get to take all the objects.
Right, but then maybe the sum of the xi vi is not maximized if you do that. You want to maximize still the sum of xi times vi, not the sum of the vi's. So if you take 1/10 of an object, you also take 1/10 of its value, not its full value. So, you know, it's kind of, the point here is that if you take the 0-1 version of this problem, it becomes a combinatorial problem. You really have to try all sorts of possibilities. Depending on how the values are and the weights are, you know, given to you, you know, it could well be that if you take one element, you know, that some of the elements you cannot take because, you know, maybe their weight is much larger. You have to work with the elements as they come. Here, you know, one possible intuition, you know, one possible was just given by you, which is, you know, you could even get the full weight if you wanted to in all sorts of possible ways. You see, you know, if you have this x1, w1 up to xn, wn, you have a lot more, you know, in the original case you have 2 to the n, only 2 to the n possibilities to look at. Here you have infinitely many possibilities by just playing around with the xi's. So if you have so many different, you know, infinitely many possibilities and it's a continuous problem, maybe, you know, there is a better way to solve this thing. And the answer is yes, and in fact you alluded to the algorithm, how you would do that. And the algorithm is the following. Suppose that, just for now, suppose that all the weights are 1. Okay? Maybe. All the weights are 1. Then what you want to do, so, you know, what you want to do is you want to maximize this x1 times v1 plus xn times vn subject to sum of the xi being less than this w. So you could, for example, take the values and sort them according to the largest value first and smallest value last. And then you say, okay, here is how I'm going to do it. I'm going to take as much as possible of the first item, right? As much as possible of the first item because this gives me the largest value. This is why I am a greedy person. I take the thing that has the largest value first. As much as possible the first item. So with this I have given up a little bit of my weight budget. Okay, so even if I take the entire item, I take 1 out of my weight budget. And then I take the second best item. I take that one and that one. You see, here is how it would work, right? I mean, suppose, you know, you put a greedy person into a room full of jewelry. Okay? All right, so you give this person a knapsack. And, you know, I've seen these movies, right? They go and try to do this and then out of a sudden the whole cave breaks down and this kind of stuff, like Indiana Jones and stuff, right? So this is the same thing. So you give him a knapsack and then this person starts thinking, oh my God, you know, I have this much weight. What can I do? What can I do? What can I do? Takes, of course, the biggest chunk. You know, oh, this is great because this thing has so much value. Just put it into the knapsack. Then the next one. Then the next one. You know, automatically through his spinal cord, he actually applies the greedy algorithm for the 0-1 knapsack problem, which turns out to be even the wrong one in this case. But you know, that's what he does. If he could take, you know, portions of these items, you know, take the, you know, maybe a diamond and, you know, cut it and then take portions of it, maybe he would then even be better off, but obviously he can't do that. So this is what we are going to do. If there are weights, if I take an item I, how much value do I get compared to the weight that this item is going to give me? That's exactly Vi divided by Wi. Vi divided by Wi is kind of a cost benefit ratio of an item. So you get a value of V, but with a weight of W, which means if the weight is small, very, very small, the value is large, that's what you want to get. If, you know, you have some item that has a large value, but its weight is also very large, you're not going to take that one, because that is not going to maximize your value. So you calculate all these Vi divided by Wi's. And then you're going to sort them in a descending manner. The biggest one first. And then you're going to pick as much as possible from the first item, and then as much as possible from the second item, as much as possible from the third item, until you have exhausted your weight budget. Do you want to see an example? Okay. So, I'm going to take the V's and the W's. I don't know, you put a value of 3 with a weight of 5. Just give me numbers. What do I put here? I don't know any. Sorry?
4, 6.
4 and 6. Okay. What about here? 1/3. Maybe you should also give me something that is the other way around. Okay. What about here?
5, 4.
5, 4. Here? 4 and 2. Okay. Maybe last one? 100 and what? 101. Okay. Good. Okay. And maybe for my capital W. So. I'm going to, it doesn't matter. Maybe my capital W is 20. I am flying economy class somewhere. I have 20 kilograms. Okay? So, the first thing I need to do is I need to sort these cost-benefit ratios. Or in fact, benefit-cost ratios. Okay? So, I have to look at 3/5, 4/6, 1/3, 5/4, 4/2, and 100/1. Well, there's a clear winner who is the biggest, right? So, which means, so actually I need to enumerate my items too. That would be item 1, 2, 3, 4, 5, and 6. So I know that V6 over W6 is bigger than, what's the next item in the list? This guy, right? So it's V5 over W5. What's the next one? That's the fourth one, right? It's still bigger than 1. So V4 over W4. What's the next one? 2/3? 2/3, 3/5? 2/3, right? So that would be V2 over W2. The next one? V1 over W1. And V3 over W3. So I sorted these items according to their cost-benefit ratios. Okay, so now I'm going to pick as much as possible from these items without exhausting my weight limit. How much of item 6 can I take? All of it. So X6 could be 1. Right, so we are going to, well, okay, so we're going to take X6 equals 1. So when I take X6 equals 1, I have given up 1 in terms of my weight, so my new weight is 19. So how much of item 5 could I take? Well, you cannot, it's between 1 and 0, so. It's the whole thing. I can take the whole thing because my weight budget is 19 and the item 5 would give me a weight of 2. So I take X5 also equals to 1. And my weight budget at this point is now 17. How much of item 4? All of it. How much of item 2? So far my weight budget is 1 plus 2 is 3 plus 4 is 7, so 13 is what remains as my weight budget. How much of item 2? All of it, right? So my weight budget went down to 7. How much of item 1? My weight budget went down to 2. This can't be right. Okay, so it's bigger than 20. That's good. All right. All right. So far, what is, so I'm going to write down how much budget I've left at every point. So here I've left, so at the beginning I had 20 left. Then I took item 6, so that brought it down to 19. Then I took number 5, brought it down to 17. I took number 4, down to 13. I took number 2, went down to 7. I took number 1, that took me down to 2. And then how much of item 3 can I take? No, you cannot take 2. It's always between 0 and 1. No, 2/3, good. So I take whatever remains for item 3. Okay? And this brings me down to 0. So this is a solution to this problem. So I try to take from the best ones as much as I can until up to a point where my weight budget that I have is strictly between what I have so far taken and what I would get if I would take the entire of the next object. Then I take a fraction of that object. That is the algorithm. So this algorithm turns out to be optimal. And you can prove it along the very similar lines as the optimality of the classroom problem, of the scheduling problem. So far I've given you algorithms that are optimal. And the third one will also be an algorithm that's optimal. You know, in a way I should also give you algorithms that are not optimal. And they exist as well. So maybe in the last 2 minutes I show you an algorithm that's not optimal. Do you want to see it? So this algorithm wants to try to solve matrix equations. Okay, we want to solve A times X equals B, which is a system of linear equations. Now this can be a difficult task because it takes O of n cubed operations. So we are going to design an algorithm that is greedy. And this algorithm does the following. So it says go through each row of A. If there is exactly one non-zero entry, okay, then so the rows will be from 1 through n, then do a column permutation. So this entry is then at column 1, or column I. Okay, so it's one non-zero entry
At column 1?
at column I, sorry. If there is one non-zero entry in columns I plus 1 through n. So what this algorithm is trying to do is it's trying to get the matrix A in triangular form without doing anything, but just by doing these column permutations. So let me show you how that would possibly work. So let's say my A is 0, 0, 3, 0, then maybe 4, 2, 0, 0, and maybe 3, 0, 3, 1, 0, 0, and maybe 3, 4, 2, and 5. Maybe my matrix is of this form. Then for this matrix, what I would do is I would go through the first row and I will find a non-zero entry. So that would be 3. So I would make a column permutation with the first and the third column. And then I go through the next row. Now remember, this after the column permutation, this is the first column. So I'm going to look at the entries outside that first column. If there is exactly one, I'm going to pick it. Then I'm going to go again through the columns. If there is exactly one entry, I'm going to pick it, and then I'm going to pick this one. So the column permutations would be, this would be afterwards, this would be column 1, this would be column 2, this would be column 3, and this would be column 4. So if you write down these things, you would find this is 3202, 0433, 0014, and 0005. After doing this, your matrix becomes...
Why do we get the 4 after 3, not the 2?
Oh, because you see, when you do this column permutation, you have to look at every row outside the column that you have marked. So this becomes the first column afterwards, right? Here he says you have to look in columns I plus 1 through n. So you would have to look at columns 2 through n, and since this is column 1, this means you have to look at the columns that are not equal to this. So you see, this algorithm made this matrix into triangular form. Once it is in triangular form, you can solve systems of equations in quadratic time instead of cubic time. Right? Now you agree that this algorithm is really, it's a greedy algorithm because it really tries to do local things, but you agree that this is not going to work. So if you can't find any such thing, if you can't find a row that has exactly one thing, one element in it, you will just fail, right? But we know that there are cases where the matrix is not of this form, but you don't fail in terms of if you applied Gaussian elimination, for example. So you see, this very simple greedy algorithm fails. Now what is interesting is that you can actually design a whole theory about what statistical properties this matrix has to have so that this algorithm doesn't fail. And you can use that in order to, for example, transmit information over the internet, even if packets are dropped, over satellite and so on. And a lot of these algorithms have been at this point standardized in many of your cell phones, just using this very simple greedy algorithm. So the greedy algorithm is not optimal. In this case, you ask, then I'm going to change my world so that in this new world the greedy algorithm becomes optimal. It's a very interesting thought. Okay, so I see you guys on Monday, and you guys know there is a midterm on Monday afternoon. And I tell again, this midterm has absolutely